All right, this is chapter 4, number 28, the one with the 3 uniform spheres at the corners of an equilateral triangle, and they gave us the distance, or the lengths of the sides of the triangle, and masses of 2 of the spheres, and there's a 3rd sphere, mass unknown, released from rest. We're trying to figure out the acceleration, and the only thing that exists in this universe are those 3 spheres. Call this M1, or sphere 1, sphere 2, and sphere 3. So 1, 2, and 3. And we know these 2 masses have values of, move this over here. Masses of, this is number 28 again. 28, chapter 4, 28. And masses of 2.8, we got 1.2 meters for the sides. So these distances, 1.2 meters, 1.2 meters, 1.2 meters, and our mass of this guy is 2.8. What was it? 2.8. So 2.8 kilograms and 2.8 kilograms. So there's lots of stuff here that we know, and we're trying to find the acceleration for what I've called sphere 3 at the top of the equilateral triangle. If you put this here or here, it doesn't matter. The problem will work exactly the same. You'll get the same result. Different direction, but same magnitude for the acceleration, and that's what we're trying to find. So I'm going to draw the 3x diagram for sphere 3. So this guy right here. This is 1, 2, and 3. So a dot to represent sphere 3. And what forces are acting on it? Well, the only thing in the universe, the only forces we're accounting for due to these other spheres, is just gravitational forces. So what will sphere 1 do to 3? 1 will pull on 3 down and to the left. 2 will, and this really messed up my picture. Clean up this, get rid of that. We know the sides are all 1.2. So 1 pulls on 3 down to the left, 2 pulls on 3 down and to the right. And that's it. That's the only thing that's exerting forces here. So I'm going to label it as such. So force of 1 on 3, and this is due to gravity, and force of 2 on 3. A little bit of quick scratch work here. If the sides are all the same, so are the angles. So this is 60 degrees, this is 60 degrees, and this is 60 degrees because we have an equilateral triangle. There's an eraser. The other thing that we're going to do here eventually is drop a perpendicular so we can deal with components. So if I do that, this will be useful. This was 60, now this is 30 degrees. That's going to matter here in a little bit. We'll come back to that. If I ever say drop a perpendicular, that's what I mean. We're just drawing a line that makes this into a right triangle. So now that's 30 degrees because it's 30, 60, 90. Okay, come back to that. Let's see if we can notice some things to make this problem easier. There's some symmetry going on. These distances are the same. So the magnitude of these 2 arrows should be the same. The equation that will govern these will be F equals big G, mass of one object, mass of the other, over R squared. Well, all the R's, all the distances from center of object to center of object are the same, so these will have the same size arrow. That's good news, because the angles are also the same. I put this on here, this is 30, and this is 30, as we kind of just discussed, because there's my drop in the perpendicular, so 30 and 30. So the components in the x direction are going to add up to 0. I'm going to do some scratch work here just to try to convince you of that. Here's this force, this F1 with its components. And now I'm going to draw F2 with its components. So here's F2. There's F2. There's F2 in the x. There's F2 in the y. So this F2x and F1x are in opposite directions and have equal magnitude, so they're going to add up to 0. So while you could prove that with the numbers that they give you, and feel free to do that, based on the symmetry, I'm not going to. If I sum the force in the x, I know I'm going to get 0. So I don't care about the x direction because they're going to add up to 0 based on the symmetry. I'm going to worry about the y direction. If you notice here while I have this picture up, the y components of these 2 forces have the same magnitude and the same direction. So if we have, making this number up, if we have 3 newtons down and another one has 3 newtons down, that's a total of 6. You just double one of them. And I'll show you that a little bit more fleshed out. If you notice that, great. So how do we get the magnitude of these forces, and what do we do next? We get rid of this picture right here, and we're going to sum our forces in the y direction. Equals mass times acceleration in the y direction for object 3. We're doing this for object 3. We do not know the mass of object 3. We can't plug that in. What forces do we have? The y component of this and the y component of this one. And I will go ahead and call up positive. So we'll have negative F1y, negative F2y equals M3AY. Right now we've got lots of stuff here and we don't know any of it. F1y. So we need to get these y components of these forces. Before we get the components, we need the overall force. So I'm going to apply this equation. Section this off a little bit here. Not very pretty. I'll go back to on paper when I have my other way to record. Let's go back and get what the overall force is, the overall length of either one of these arrows. Because again, because of the symmetry, they'll have the same magnitude. We've already discussed that. So force of 1 on 3 will equal big G, the mass of object 1, times the mass of object 3, because those are the two objects that we're talking about the gravitational force, over r squared. Well, we know what G is, 6.67 times 10 to the negative 11th. Get a little more space here, I guess. And we know what M1 was, 2.8 kilograms. We don't know what M3 is. Divide by r squared, which was, oh, I went and erased it from all of them. Let's see here, what was it again? 1.2 meters squared. So we can turn this into some number. It's something times M3. And that's the force of 1 on 3. That is not the y component. So we're going to have to get the y component. How are we going to do that? Let's check, make sure this is all on the screen here. See how much room I got? I've got a little bit of room out over there to the right. Okay. How do we do that? Well, if I want the y component, it's either sine or cosine of one of the angles. So I'm going to put this, typically you wouldn't put this on a free body diagram. I'm doing this to save space up here. Okay. This is, we said, 30 degrees. So if we look at the y, if I dot this in here, the y component is adjacent. The y component's adjacent, so we'd use cosine. So if I want to turn this into the y component, all I have to do, just the y component, is multiply by the cosine of 30 degrees. So cosine 30 degrees. At this point, this is just some number. You know this, you know this, you know this, you know this, times M3. You now have what this is. Well, we've said based on the symmetry, these are the same. If you run through this whole process, make the M1 and M2 and do the same exact thing. You'll get the same number because M1 and M2 are equal and the R's are the same. You'll have this same thing again. So to simplify here, I'll take 2, because these are the same thing, times this equals M3A3. So 2 times 6.67 times 10 to the negative 11th, and I really should put units on this, I apologize. Newtons times kilograms squared, newtons times meters squared over kilograms squared. The units will work out. So Newton, we got some room out here. Newton times a meter squared over a kilogram squared times 2.8 kilograms times M3 times cosine of 30. And again, you can just turn this into a number. See if that's fitting on there. It is. Going downhill quite a lot. Next one will be cleaner. Over 1.2 meters squared. 1.2 meters squared. And all of this will equal M3 times A. Lucky for us, the M3's cancel. There you go, done. Just multiply this, divide by the 1.2 squared, and you should get the acceleration. And it should be negative. Somewhere I lost a sign. Here we go. I got 2 of these, but they are negative. And then my magnitude will be positive. Because we got, this is like negative x plus negative x, negative 2x. These are just variables that are the same. So negative 2 times the whole thing. And you should get the acceleration. Lots of little tricks there. You don't have to do the tricks. If you want to formally sum the forces in the x and show that they add up to 0, that's fine. When you do the x component for the force, instead of using cosine here, you would have this part identical, because this is the length of that arrow. It's the length of that arrow, but instead of multiplying by cosine, to get the x component, you multiply by the sine of 30. So you could do the x direction as well. They'll end up being the same magnitudes, just like these two y components were different magnitudes, but the same in the x. But since they're in opposite directions, they'll add up to 0. It's a little bit messy. If you still have any questions on this or want to see it done with more steps, just stop in after school. Allow maybe, if you understood the free body diagram, allow 5 minutes. That's how longer it should take. Thank you to Mr. Kravis for lending out his room.